Warm greetings. I am Dr. Muthuselvi. So let us discuss on pipelining concept, which is very important in computer organization and architecture. See, in real world, we are many times using the parallelization concept. So while we are watching the TV, we are eating, listening to the music and eating, like that. Many activities we are doing in parallel. So that parallelism concept is brought into the computing system, and that's what the pipelining. Let us look at the basic idea. See, usually the speed of the computing system, that is the speed in which the execution of programs is carried out, it depends on the faster circuit technology. Of course, the faster circuit technology is used to implement the processor and the main memory. So now we are going to arrange the hardware in such a way that more than one operation should be performed at the same time. That's where we are going to have the parallelization concept. Another one, the number of operations performed per second, that can be increased. So we are going to make the changes in the hardware to address these two. Of course, the time needed to complete one operation, that is not changed. So we have the concept pipelining. So it is the effective way of organizing concurrent activity in a computer system. For example, see, let us take the manufacturing plants. So there we have the pipelining. Actually it is called as assembly line operation, where it is used in automobile manufacturing. So here the different activities are carried out at the same time. So that is the example for the pipelining. So in a computing system, let us have some instructions, that is ij plus 1, ij plus 2, and each and every instruction, that is it is taking 5 clock cycles. That is, we can say fetch, decode, compute, memory and write. Ij plus 1, it is also requiring 5 clock cycles, fetch, decode, compute, memory and write. So now if we apply the concept of pipelining, so simultaneously more than one activity can be carried out. For example, when ij instruction, it is fetch, then ij plus 1, ij plus 2, no activity is carried out. Then the second stage, it is decoding the instruction. So when ij instruction is decoded, instruction ij plus 1 can be fetched. So decoding of ij and fetching of ij plus 1 is done parallelly, that is at the same time. Then during the third clock cycle, the computation, that is of the instruction ij is taking place. Now decoding of instruction ij plus 1 is taking place, and fetching of ij plus 2 is taking place. So this is what the idea in the case of computing system. This is the case for ideal. Let us assume we have 5-stage pipelining. So here in stage 1 we have instruction fetch, in stage 2 we have source registers, in stage 3 the logical and arithmetic operations are carried out by the ALU unit, in stage 4 the memory access, the result can be stored into the memory, and in stage 5 the result will be stored into the destination register. So here the instructions are to be fetched and executed one at a time. So here we need 5 clock cycles to complete the execution of one instruction. So now in the pipeline stage, actually we have instruction fetch, then we have the interstage buffers B1, B2, B3 and B4. So here we have the instruction decode, we have the compute which is done by the arithmetic logic unit, then the result actually it is stored into the memory. So, the result is to be taken from the memory and stored into the required register file. So, these are the different stages in the pipeline we have. So, here let us see the data path, operands and results. Actually, this is what the data path we are going to have for the operands and storing the result. And we have the source and destination registers. Of course, we have the control signal. So, without the control signal, it is not possible. So, we need the control signal. So, in the first stage of pipelining, let us see what is happening. So, a new instruction that will be fetched using the program counter PC. So, we know program counter stores the address of the next instruction to be executed. So, the processor gets the address from the PC and it fetches the instruction from the memory. So, the information like register addresses, the data, the operations, all these that can be carried through the pipeline as each instruction proceeds from one stage to the other stage in the pipeline. So, here the information actually it is held in the interstage buffers. For example, register RA, register RM, register RY. Let us see one by one the role of the interstage buffers. Let us start from B1, that is interstage buffer B1. It feeds the decode stage with the newly fetched instruction. So, after the instruction is fetched, it is decoded. So, that is fed by interstage buffer B1. Then we have this B2. So, now this buffer it feeds the compute stage with the two operands read from the register file, the source and destination register identifiers, then the immediate value derived from the instruction, incremented PC value which is used as the return address for the subroutine call. Even settings of control signals which are determined by the instruction decoder, they are also available here, and setting for the control signal which are moving through the pipeline to determine the ALU operation, the memory operation and the write whether the write into the register file. So, all these are given by this buffer B2. We have this interstage buffer B3. Let us see what it is doing. So, here it holds the result of ALU operation. For example, after the addition, we have the result and that is held in the B3 buffer. So, data to be written into the register file or an address that feeds the memory stage. And to get the access to the memory, we need the data from B3. So, here it holds the data, which data is to be written into the memory and the data which is to be read from the register file. So, after the decode stage, of course, we know the processor knows the data to be read from the register file. So, that is given by this buffer B3. It also holds the incremented PC value passed from the previous stage. So, if the return address is required during a subroutine call instruction. So, that is also stored by buffer B3. Let us look at buffer B4. So, it feeds the write stage with the value to be written into the register file. So, the value may be the result of the operation completed by arithmetic logic unit, or it may be the result of the memory access stage, or it may be the incremented PC value which is used as the return address for a subroutine call. Of course, we have some issues with the pipelining. Let us discuss. So, suppose a new instruction it is not able to get the value or get the operand in each and every cycle. So, let us assume ij and ij plus 1 are two instructions. So, here the destination register for instruction ij, that is the source register for instruction ij plus 1. So what is the meaning? The result stored in the particular register, that is the required source for the next instruction. So now the result of instruction ij, so it is available only after cycle 5, because after cycle 5 only we have the data available in the register. So now let us take ij plus 1, but it needs the data to be computed in the cycle 3. So now the data is not available for instruction ij plus 1. So now it may use the wrong value, that is some garbage value in the register, so which leads to an incorrect result. So the instruction ij plus 1, if it is required to use the correct value, then it has to wait. So it cannot read operand till cycle 6. So here it must be stalled in the decode stage for 3 cycles. So when the instruction ij plus 1 is stalled, the next instruction, it cannot also proceed to further stages of pipeline. So this condition actually we are going to call that as hazard. So it is any condition that causes the pipeline to stall. So one example, source operand of one particular instruction, it is not available during the computation. So now there is no other way for the instruction to proceed. So it has to wait, that is stall. So this is what called as a hazard. Now in hazard we have one particular hazard called as data hazard. So it is a situation in which the pipeline is stalled. Why it is stalled? So the data which is to be computed, so it is now not available or some delay in getting the data. Due to this we have a hazard which is called as data hazard. Of course we have to find out the solution. One is operand forwarding. Let us see what is operand forwarding. Let us take one example. So 2 instructions are there, add R2, R3, hash 100. So here 100 is one operand, another operand is available in R3. These two are added and stored in R2. Then we have another instruction, subtract R9, R2, hash 3. So 3 will be subtracted from R2, result will be stored in R9. So here we have the data dependency, that is the source. One of the operands for the second instruction R2, but still it is the destination for the previous instruction, it is available only during clock 6. So the second instruction, it depends for data for the the previous instruction. So now we have a pipeline stall, and that is due to data dependency. So only, that is after the ALU completes its operation, then only the data will be available. So now the value, it is to be loaded into one register RZ, which is a buffer B3, interstage buffer B3. So now instead of going for stall, we can have a hardware such that it forwards the value from register RZ to ALU. So instead of writing it into the memory and writing into the register file, then for taking the operand to the ALU, what can be done? From the register RZ, that can be directly forwarded to ALU, and that is called for operand forwarding. See, this is what we have. So add instruction. So fetch, decode, compute, memory and write. So without operand forwarding, so till this clock cycle, this instruction, it should wait. But because of operand forwarding, what is done, as soon as the data is available, after the compute cycle data is available, so now that will be forwarded to the arithmetic logic unit, so that the next instruction can get the value in the register R2, and this is what we call operand forwarding. See, in the hardware, this is how we are going to make the change. So, see here, RZ, from RZ it will be moved to RY, again it will be going to the register file. From there, the data will be sent to the arithmetic logic unit. Because of this only, more cycles are needed. Now, we are doing the change in the hardware, so that, so in the arithmetic logic unit, I have the value RZ, and that RZ value given as the input to the registers, that is from the multiplexer A and B, it is given as one value, so that if it is required, that can be taken directly. So, instead of taking it through the register file, the operand is now forwarded, and we call that as operand forwarding, and by this we overcome the issue of data hazard. Another one, through using NOP, that is no operation instruction, which is done in the software, we can find the solution for data hazard. Let us take the example, add R2, R3, 100. I have subtract R9, R2, 30. So, these are the instructions we have used. So, between these two instructions, I am adding 3 other instructions NOP. So, during NOP, that is no operation, nothing is done in the computing system. The processor still simply it has to wait. So, now I have added. So, let us see the pipeline execution, how it is taking place. So, add R2, R3, 100. So, fetch, decode, compute, memory and write. So, these are the 5 stages. Then for NOP, again I will be having the pipeline stages like this, NOP, NOP. So, up to this one, nothing will be done in the pipeline. So, during clock cycle 5, fetching of this instruction starts. So, here only it needs the data, that is R2, that is compute. So, now the completion is, that is the first instruction is completed. So, now the data is available. So, by including NOP operations, we can overcome data hazard. So, in summary we can say operand forwarding, insertion of NOP, we can overcome data hazard. But including the NOP operations, it lead to increased code size. So, we are including 3 more instructions. That will be a burden. Automatically the execution time, that is also increased. So, it is required to optimize the code, and which will be done by the compiler, so that the performance of the computer will not be decreased. So, one solution we can have, it is reordering the instruction. When we have many number of instructions, the instructions can be reordered, so that the execution will not be affected at any time. Thank you.